All right, this is going to be your lecture video, the second lecture for chapter 2. What we're going to do is we're going to start it off with a video. Now, this video, I'm going to go ahead and link it on our Canvas shell, so you can start with that. But it's going to be a video that's put on by the TED Talk that's going to be looking at our periodic table. So go ahead and watch that one. It takes about 5 minutes. And so once you have that, then we're going to talk a little bit about that today. So your video was all about the periodic table. Now, the periodic table does come in a variety of different types, right? We can have some that are arranged like this. We can have some that are arranged like this. But it's all based on this idea that some elements are similar to each other. So while we have different versions of it, things that are trying to kind of look like each other, the most common one that we see is one that looks like this. And so this will be the primary one that we use for our course this semester. We're going to use a traditional one here, where it looks kind of like this square. All right? Now, the way that a periodic table is set up is that it's based on this concept of periodicity. So when they were first developing the periodic table, what they noticed was that there were several families of elements where they behaved in similar ways. They had similar reactions. So they had similar reactions. And so the scientists at that time started to group these together, and they started to see a pattern as they would repeat and repeat and repeat. One of the first ones that they found were these non-reactive gases. So ones like hydrogen, or not hydrogen, sorry, ones like helium and neon and argon. That we had these repeating ones where they kept coming up with a gas that was not reactive no matter what we tried to do with them. And so this is an idea called periodicity. So Mendeleev started to summarize this. He started to build these tables where we started to group them together. So there's repetition of our responses. And so when we talk about the periodic table, there's a couple of terms that we want to be familiar with. The first one is the name period. So period is what we call a horizontal row on the periodic table. So things like hydrogen and helium are in the same period. Groups, on the other hand, are the vertical column. So hydrogen and helium, they're in the same period, but helium, neon, argon, those are all in the same group. So a chemical periodicity is kind of associated with the groups. The chemical, the periods have more to deal with how often those, how long it is until the groupings repeat, until that periodicity repeats. Now, you'll notice at the top that our periodic tables do get numbered, and each of those groups have a value associated with them. Now, some will number them all the way across like this periodic table where we have 1 over here and we have 18 over here. Others will start to use this 1A, 2A, 3A, and so on. Now, what that means is what we call our main group elements. So our main group elements, they take on these first 2 columns here and these last 6 columns here. They get their name because they were some of the first elements that we discovered and categorized together. So they follow one set of rules when we look at their the electron configurations, which we're going to talk about a little bit later. On the other hand, our transition metals is this grouping right in here. Those are our transition metals. The other 2 parts that we would talk about is our lanthanides and actinides. So our lanthanides are here, and our actinides are here. And so the lanthanides are this entire period, and the actinides are that entire period. So when you're first starting, there is an equation sheet for our course, and I've gone ahead and I've linked it onto this lecture slide here. You can go through and you can start to label and become familiar with your periodic table. You can add in your colors about where we have our main group elements, where we have our transition metals. And you can start to work with those to build them a little bit. So that way you can be familiar with it. Now, when you get to your exams and your final exams, you will start with a fresh periodic table. So you don't want to be too reliant on those things that you add in, because you won't have those notes with you when you get to the exams or the final exam. So just keep that in mind as you're working through. So the next thing that we're going to do is on our periodic table, we're going to separate them into our metals and our nonmetals. So our metals are going to be all of the elements that when we find them at room temperature, they behave like a metal. And so that's going to be everything outside of this grouping here. So our metals basically start with aluminum, gallium, and then tin. And they jump down to bismuth and polonium. And so they kind of make a wall over there. Our nonmetals are all of these ones in our green. So they behave a little bit differently in their chemical reactions, which is why they get a different response. So they're going to be our gases for a lot of them. So things like oxygen and nitrogen and helium and neon. But they can also be some non-gas materials, but they're still nonmetals, things like carbon, sulfur. Right? So the top right is basically our nonmetals. Everything else is going to be our metals. The only exception to that is helium, or not helium, hydrogen, over here on the left-hand side. What you'll notice with hydrogen is sometimes it behaves like it should be over here, right next to helium, and sometimes it behaves like it should be over there on the far left-hand side, where it's located on this picture. It kind of goes back and forth depending on its physical properties, so it's a little bit different in that regard, but we will almost always write it over here on the left with lithium, but just know that sometimes it breaks those rules. Now, separating our metals from our nonmetals are these 7 metalloids. It's boron, silicon, germanium, arsenic, antimony, tellurium, and actinium. Right? And the reason why they're called metalloids is that their properties are right there in between metals and nonmetals. So they're taking on a little bit of both. And so that's why we have that there. And so most periodic tables, what you see is that there's kind of like this staircase that edges its way down, and that staircase is separating our metals from our nonmetals. Now, you do want to be comfortable with that and familiar with where that cutoff is. A lot of times it's easy to figure out whether you should be on the metal side or the nonmetal side by looking at an example. So if you wanted to think about a gas, right, some gas that you know, maybe that's oxygen, maybe that's helium, maybe that's neon, but all of those are gases. And so when we look on that line, we can always figure out which side should be the non-metal side because it will have those gases that we know about. On the other side, if we think about what metals we might know, maybe we know about iron right over here. Maybe we know about gold and silver. And we can use those to piece together the other parts about where our metals should be. So you just have to remember where the cutoff is, and then we can always determine which side should be the metals and which side should be the non-metals. Metalloids you do have to memorize because there's not really a great way for that, but they all touch on where that cutoff value is. Now, metals, the reason why they get their name or why we categorize them is there's some physical properties that they all share. Right? Most of them are shiny in their luster, so that means that they take on the shiny appearance when you have them as an element. They conduct heat and electricity very well. This is why all of our wiring is generally made with some type of metal, things like copper or steel. And all of them are going to be solid at room temperature except for mercury. Mercury is going to be the exception to that rule. Mercury is our one liquid at room temperature. Metals also do a great job conducting heat, which is why we use them often for things like pans. They conduct that heat into our food. But why you don't want to do something like drink hot tea out of a metal cup. Unless it's insulated metal, right, where we have a layer between those two, like a thermos, it can actually get really, really hot, and you can burn yourself if you pour hot water into a metal cup. Nonmetals, on the other hand, they take up the right side of the periodic table, and they can take on all different types. So we have solids, we also have liquids, we also have gases. Now, bromine is an example of a liquid that we can find. Bromine is sometimes classified as a gas because it actually has a very low boiling point. And so that's why sometimes people get it labeled as a gas instead of a liquid. But nonmetals can come in all three states. Right? We do have some solids in there, but we also have some liquids. We also have some, or we have one liquid and we also have some gas. Now, the ones that are kind of in between those metalloids, it's because they share some metal properties and some non-metal properties. And so there are these in-betweens. And so we'll see that in the chemistry that they do, you'll learn about them a little bit later on. We cover a little bit of it in 121. They take on these in-between properties because they behave a little bit like metals, but at the same time, they also behave sometimes like non-metals. From there, we should be familiar with several of these common group names for these groups. And so what that means is that when we looked at that periodic table, some of these groupings are going to have a name associated with them because they're so well known and because they have such interesting chemistry. There's a shorthand name for some of them. So the first one we're going to talk about is our noble gases. These were actually the ones that helped us pioneer the periodicity lab, or the periodic lab, law by Mendeleev, about how we developed the arrangement of the periodic table. And what these are all going to be gases, but they're going to be unreactive. They're not going to respond to many materials. This is why we use things like helium to fill a balloon, because it's so stable, it doesn't react with many other things, and it can be used like that. Plus, it's lighter than air, so it will float. Whereas other countries might have used hydrogen when they were filling their balloons. That's more common when we talk about like the Hindenburg. And so that was more like the blimp style balloons. Hydrogen is not a noble gas. Hydrogen does react quite strongly. And so that's how we got the Hindenburg explosion, right? Was because as a gas, it was lighter than air, but it did react. It was flammable. Helium, on the other hand, does not. Another type of noble gas is neon. We see these in what we call neon lights. So those electric signs that you see, they normally have that red color. Argon is another one. Argon is used when we store a lot of material. It's a small part of our atmosphere currently. And then we have krypton and xenon as well. So these are all gases at room temperature and room pressure. And they're not very reactive. So they kind of get their name noble gases because they don't really want to interact with any of the other elements. They stand alone by themselves. Alkali metals are kind of the opposite. So they're group 1A, and they are very, very reactive metals. So these are things like lithium, sodium, potassium. Now, lithium and sodium and potassium, they're so reactive that if you put them in water, they react violently. They make a big explosion. Right? It leads to some very interesting chemistry on their part. They make a lot of vigorous reactions between the three of them. And so that is something that is there. Now, I'm going to link a second video down below this lecture, where we're going to look at the reactivity of the alkali metals, and we can see what happens when we put a piece of lithium and sodium and potassium and rubidium into things of water. Alkali earth metals is our second group. So this is group 2A. Now, alkali earth metals are fairly reactive, but not quite as reactive as our alkali metals. So that's what makes them different. Now, we're going to see some of this in our labs as we keep moving forward. We're going to start to react some of our materials. Sometimes we'll put the calcium inside of water and we'll see what happens. We might use other metals inside of water to see what happens. But we'll start to see some of these reactions. Now, alkali earth metals are fairly reactive, but they're not as reactive as alkali metals. So if you wanted to think about it, this one, group 1A, is our alkali metals, and they are very reactive. Group 2A, this was our alkali earth metals, and they are not as reactive, but still react. The third group that we've talked about so far is our noble gases over here, and these ones are not reactive. Oh. Now, reactivity doesn't just go from the left to the right, but it does show us that at these extremes, we're kind of going to get these extreme responses, right? So ones all the way at the left are going to be very reactive. The one all the way at the very right is not reactive, but there are some in-betweens there. So we're going to talk about those. So we've talked about alkali metals. We've talked about alkali earth metals. Our next one is going to be what we call as halogens. Now, halogens are very reactive, and they are group 7A. Now, halogens are so reactive because they are involved in a lot of different chemistry as they try to become like the noble gases. And so we're going to talk about that when we get into bonding. Now, these halogens are things like chlorine or iodine, which you might have heard. It also includes fluorine and bromine as well. Now, because they are so reactive, we can use them in a lot of different circumstances as we're moving through our different chemical options, right? So our halogens now, as we go back to this, our halogens are going to be this group right there, group 7A. So we have 4 different ones that we're talking about. And so remember that our groups are always going to be top to bottom, those family of elements. Side to side is our periods, and they don't get those common group names. The very last one that we're going to have you guys remember is group 6A. Group 6A is similar to the alkali earth metals in that they are like halogens, but not quite as reactive as halogens. They're called cachalogens. So it's like a C in front of a halogens, but there's also another C over here. So these cachalogens, that's the common name for group 6A here on periodic table. No, hold on. So there we go. Group 6A, this one here, is going to be our cachalogens, and they're going to be not as reactive. Still somewhat reactive, but not nearly as reactive as the halogens. And so those are our common groups. Now you want to feel comfortable with these names and these concepts. And so if you have like a partner that you want to work with, or you have a study partner or anything like that, one thing that you can do is you can try to play a game. Now it's called the periodic game, or periodic needle in a haystack, right? And so what you can do is that you can work with the partner, and one of you would choose an element, and the other one is going to try to guess what that element is. Now, you want to go through and you want to kind of give them ideas about what they would be. So you could give them the period number, you could give them the group number, you could give them the group name, and you guys would try to work your way through that to try to find your different elements. You just want to start to become familiar with your periodic table. start to feel familiar with identifying things. So as an example for this, I'm going to tell you that I'm choosing an element and it is going to be in group 6A. I could then tell you that it is in period 4, and we should be able to identify what our element is. And so if you figured out that it was tellurium, Te, then you would be correct. And so that's kind of like how you can do that. The other one could have been, I could tell you that I am thinking of an alkali earth metal. Now that alkali earth metal, I'm going to say that it is in period 5. So that's going to be our strontium. Now I realized that I made a mistake when I was talking about tellurium. Tellurium is not in period 4. Tellurium is in period 5. So the first example, it shouldn't have been tellurium. It should have been selenium. I miscounted when I was going down. And so if we jump back and we look at a periodic table, we can see how that mistake happened. So I'm going to go ahead and clear this up. So we knew that group 6A was this one here. And when we're doing our periods, we have to make sure that we include this top row here. So I said that I was in the 4th period down. And so I just quickly went 1, 2, 3, 4. But that's not true. That's not the right counting of my periods. My first period is this one up here, the period that hydrogen and helium is. So oxygen is already in the 2nd period, 3, 4. So that's why it should be selenium, not tellurium. And so that was the mistake that I had made. And so you don't want to make those same mistakes. Don't be like me, be better than me, right? And so that's how we can do that. So now as we're starting to get familiar with these elements, the reason why is that we want to start being able to develop our formulas. Now, our formulas, we're going to start by introducing what a chemical formula is. The chemical formula is made up of these different subscripts and our elements to tell us how many atoms of each element are present inside of that compound. So these little numbers that come to the side, those subscripts, are telling us the number of atoms present. So when we have NH2, this is 1 nitrogen atom and 2 hydrogen atoms coming together. Now they're important because when you change those numbers afterwards, the number of atoms can really change your chemistry. An example of this is our water and our hydrogen peroxide. Now, hydrogen peroxide you might have worked with already before. You might have it at home. We use it when we want to sanitize cuts. Right? It helps clean those cuts out. Water, we definitely are familiar with. You've probably drank lots of water in your lifetime, I would hope so. And so water is made up of 2 hydrogens and 1 oxygen. So in this case, our white balls that are drawn in here, that's going to be our hydrogen, and the red is our oxygen. For hydrogen peroxide, instead of having just 1 oxygen, it now has 2 oxygens, and so that's why it has 2 of them kind of connected here. So there's 2 atoms of that. And just that extra addition of an oxygen atom changes its properties. We see this again, carbon monoxide versus carbon dioxide. Carbon monoxide is 1 carbon, 1 oxygen. Carbon dioxide is 1 carbon and 2 oxygens. Carbon monoxide is that silent or is odorless and smell or odorless gas that happens when you guys get like an incomplete combustion. So like when you have a stove that's burning, things like that. It's why you need a carbon monoxide detector inside of your house. Because when this happens, you can actually suffocate if you inhale too much carbon monoxide. Carbon dioxide, on the other hand, is what you guys exhale. It is toxic. If you get a whole bunch of it, it still will suffocate you, but it's a much, not nearly as toxic as our carbon monoxide. Now, for our chemical formulas, molecular compounds are going to be ones where their material is composed of groupings of these atoms. And almost always they're containing our nonmetals. So some materials will show up as a set, like hydrogen. Some materials will show up only as like a never-ending grouping of materials. Those are going to be things like our salts or like a lot of our elemental substances. And that has to deal a lot more with our bonding that we get into. But for now, I just want you to think about our materials as being kind of like these molecules. So what we're seeing in like things like water or carbon dioxide is we're seeing a set of atoms connected into a bigger team. So we get two hydrogen atoms connected into one hydrogen molecule. We have one carbon and two oxygen atoms connected into one molecule of carbon dioxide. And so these chemical formulas are giving us these molecular compounds. We're giving their kind of recipe to make their molecule. So the types of chemical formulas that we have is two. One of them is going to be called an empirical formula, and the second one is going to be called the molecular formula. So the molecular formula is a little bit different than our empirical one, because the molecular formula tells us the exact number of atoms that you need to make that one set of your team. So let's say that our set is going to include two oxygens and it's going to include two hydrogens. Now this entire thing is one molecule. So there's one set. And this is hydrogen peroxide. So its molecular formula would be H2O2 because you need two hydrogens and two oxygens in order to make that one molecule of it, to make that set. The empirical formula is different. The empirical formula is only concerned with the ratio of the atoms. And so our empirical formula is going to be H and O, one hydrogen and one oxygen, because they will always show up in a 1-to-1 ratio. Empirical formulas matter a lot more when we first start doing experiments, because sometimes we will know what elements are there and the ratios of those elements, but we won't know how many molecules we might have had to be breaking apart in order to do it. On the other hand, molecular formulas like H2O2 can be really handy because it helps us clarify different materials that have similar ratios based on how many of them you have to piece together to make that actual molecule or the actual set. We can know the molecular formula of a compound, then we can figure out the empirical formula. But just because you know the empirical formula doesn't mean that you can know the molecular formula, which seems like a lot. So let's do some practice with it. Consider the following ones. We have SO2, B2H6, CO, and C4H2O2. Which of these formulas could be only a molecular formula? So take a moment, you think about it. So the answer should be B, B2H6, and C4H2O2. Those can only be a molecular formula because their ratio can always be simplified. We could have BH3 and C2H1O1. And so since we can simplify them, then they cannot be an empirical formula. That means that they have to be molecular. Now, when you see formulas written, if they don't have a number written, then that's standing in for that one. You can write the one if you like, or you don't have to. You can leave them out. Either one is fine. The important part to remember is that the number to the bottom right goes with the element in front of it. So don't interpret C4H2O2 as 4 hydrogens and 2 oxygens. It really is 4 carbons, 2 hydrogens, and 2 oxygens. So keep that in mind. Let's look at our next example. So using those same 4, which of these formulas could be either a molecular or an empirical formula? So they could be either or. That answer is going to be B. The only ones that it could be is our carbon monoxide and our SO2, sulfur dioxide. The reason for this is CO and SO2, they're in the lowest ratio. So that could be an empirical formula. But it could also be a molecular formula because they also could be that same structure. So pretty much all of our different formulas could be a molecular formula for now, but not all of them can be an empirical formula. And so we want to keep that into consideration. Now, when you picture molecules, there's several different ways to do it. One of them could be our formulas. Other times we start to draw them out in terms of our structures or our 3D ones. This is going to be something that we will continue to work on throughout the class. Right? So you don't have to worry about how they're all connected now. We're just starting with this first one. But we will be eventually adding on to them. We eventually work on something like this, our structural formulas, which we're going to call Lewis structures when we get into there. Later on in this course, we're going to get into the 3-dimensional shapes of them as well. Right? And so all of these are just different ways to help us visualize how our atoms are being connected inside. So inside of your book, when they do these drawings, those drawings are there to help you visualize them. Now, for our elements, there are 7 elements where when they naturally occur, they occur as what we call a diatomic molecule. They show up as 2 atoms. That's going to be hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. So if we jump back to our periodic table, we want to make sure that we know how our elements show up. So H, O, F, N, Cl, Br, and I, those all show up as diatomics, H2, N2. So now when we talk about elemental nitrogen showing up by itself, then we should be able to know that it shows up as 2. It shows up as a diatomic molecule. On the other hand, if we're talking about an element that's not like that, let's say we're saying helium, then we know helium shows up by itself. Or aluminum, aluminum shows up by itself. So only those 7, when we see them, they're going to show up as what we call a diatomic molecule. And so that's going to be an important part when we start working with our chemical reactions and translating them over. So those are our 7 that occur. Now, from there, the other part that we're going to look at is that every number has its place. And so this is an important part to know from this chapter, is every number has its place. And so what I've tried to do is give you an example so you guys can see it, and so that way we can color code them. You can kind of make sure that we're on the same page. So the small numbers to the right is telling us how many atoms of that element in front of them there are. So in this case, there's 3 of those oxygens. Numbers in front that are big, this 4 and this 3, they're telling us how many sets of that chemical formula we have. So in this case, this 4 here is not saying that we only have 4 calciums. It's actually saying that we have 4 of this entire grouping. So it's kind of like the difference in talking about a basketball team. If we wanted to describe a basketball team, you might say that you have 2 guards, 1 center, and 2 forwards. Now, if we have 2 basketball teams, we would say that we have 2 of that entire set, 2 basketball teams. If we said that, well, we're not going to play with a center, we're going to go with small ball, we could take out our center, and we could then go up to maybe 3 guards, right? So that's why each of those placement of those numbers matter, is it gives us different pieces of information. Now, we've already talked about our mass number. That's the one that comes in front of the element, but it's going to be smaller. It's going to be that superscript. So it's up top. This spot down below would be our atomic number, though often we don't write the atomic number because we don't need it there. The last part is behind it. That's going to be our ion. So that's the charge of the atoms. And so we're about to get into that coming up in our next section. So every number has its place, and so you want to make sure that you understand where you should be recording all of those numbers. Now, we haven't gotten quite to it yet, but I'm going to talk about why we have parentheses. So parentheses can show up inside of a chemical formula. That part is fine. Sometimes why they show up in that chemical formula is because this grouping on the inside is kind of behaving like a set inside of our larger molecule. So we have like a repetition of it there. So this 2 on the outside, that 2 is going to everything inside of those parentheses because it's coming after it. So that 2 is not just going to the oxygen. It's going to both the nitrogen and the oxygen. So if we wanted to get rid of it, it would be calcium, and it wouldn't just be NO6, it would be N2, because that 2 should go both to the nitrogen, and it should go to the oxygen. O, and then 3 times 2 is where we get that 6. So small numbers outside of the parentheses go to everything on the inside. Okay. So the next part that we're going to talk about is our ions. So ions form in a couple of different ways. Ions can happen when we gain more electrons than we normally would. It can also happen when we lose electrons compared to what we normally would have. So anytime that you have a change in your electrons, you become an ion. It means that you have an electric charge. Now, inside of that, ions can then be classified based on if they have a positive charge or if they have a negative charge. So positive charge are called cations. How I remember that is cations are very positive because cats are very positive. Now, cations are going to be a positive charge because they've lost electrons. Now, we can think about that because electrons are negatively charged. So if we have too much positive charge, it means that we must have lost the negative things. So the more electrons we get rid of, the more positive our atom or our ion will become. Now you'll notice that when we write our charges, the normal format to how we do that is we should write the number first and then the symbol. So sometimes people just put the plus sign, or you can put 1 plus. That's fine, but generally speaking, do your number first and then the symbol. It really becomes helpful when you have the negatively charged ions because it's easy for that negative sign to get mixed in with your element. It's better when it comes afterwards. Now, speaking of negative ions get their own name. So cations were positive, anions are negative ones. And so anions happen because we've gained electrons. We've picked up more negative things. Now, primarily, cations are formed by metals, and anions are formed by nonmetals. That's not set in stone. You can break that rule, but that's a good concept to start with. And so the reason why is that metals lose electrons. Metals have what we call low electronegativity. That's their ability to attract electrons. And so their low electronegativity, they don't attract many electrons, and they have a low what we call ionization energy, their ability to lose electrons, makes it easy for them to go from being a normal element to losing electrons and now becoming a cation. So metals lose electrons. Now their goal is they're going to try to get rid of these electrons until they can become stable. And what we mean by stable is that they have what we say a full valence shell of electrons. We'll get into that a little bit later when we do our electron configurations, but just understand that these metals are basically trying to give away electrons until they can become more stable. Nonmetals, on the other hand, they're going to do the opposite. They have what we call a high electronegativity, and they have a high ionization energy. And so they have a high ability to attract electrons, and it's hard for them to lose electrons. And so they are going to gain electrons. So they are going to try to fill their valence shell, not by getting rid of electrons until they go into a more stable state. They're going to try to gain electrons to fill the gaps in their holes until they have a full shell on the outside. So that means that our metals should form cations. And this is happening because they're losing those electrons. So let's look at sodium as an example. Sodium is losing one electron here. This one is going to be our electron. And so when it loses that one electron, it's going to go from being a 0 in its charge to a 1 plus. So if we wanted to look at that, or have 11 protons because it's sodium, it normally would start with 11 electrons and be neutral. But because it's gone ahead and it's lost an electron, instead of being 11, we should have 10 of them. And so our net charge is going to be a positive 1. And so it is an ion, but specifically it will be a cation because it's positively charged. Anions, on the other hand, anions form because we are going to gain electrons. So nonmetals gain electrons, and so they're no longer neutral. And so sulfur is an example of this. Sulfur is gaining 2 electrons. And you can see we put that 2 in front because each electron is by itself an individual particle, but we have 2 of those individual particles, kind of like the 2-team example. And so we're going to change our charge. So instead of just having 16 electrons, like it would when it's neutral, we should now have 18 electrons, giving it an electron charge of minus 18. And so it has a net charge of minus 2. So once again, it's still an ion, but specifically it is going to be referred to as an anion. So positively charged ions are called cations, negatively charged ones are called anions. And based on how many electrons you gain or lose indicates your charge. Now, from there, we are going to be practicing with just our main group elements. So we're going to be looking at just these ones here. You can see that most of our metals will form the plus ones. Our non-metals will form our negative ones. The transition metals here follow a different set of rules about how we can kind of figure out how many they gain and how many they lose. So we're going to be getting into that in a little bit. Now, when they lose electrons or when they gain electrons, you can kind of imagine them as being like our periodic table. And so when they lose an electron, they start to act a little bit more like an element that was before them. So in this case, beryllium would take on this box here. So when beryllium loses an electron, it goes from having 4 electrons to having 3 electrons. Now, lithium normally only has 3 electrons. So our beryllium plus 1 is behaving very similar to a lithium. Now, when lithium loses 1, it goes from being 3 electrons to 2 electrons. So lithium plus, instead of being here, starts to behave like the element that has just 2 electrons, which is our helium. So when you lose electrons, you can imagine it's kind of like you move left on your periodic table towards the element that comes before you. All of these ones here that stop, what they're doing is they're moving to that row in front of them. Now, what you notice based on the ions that we make is that everyone's basically trying to get to our noble gases, because our noble gases have what we call a full valence shell, which is why they're so stable and they don't react with many things. So all of our different elements, they're trying to form these ions to look like a noble gas. So hydrogen will try to gain 1 electron so it can look like helium. Lithium would try to lose one electron so it can look like helium. Fluorine would try to gain one electron so it can look like neon. It will look like it has 10 electrons. Oxygen will try to gain 2 electrons. One electron moves it towards fluorine, the second one will move it towards neon, and so on. So that's kind of how you get this idea about where we're forming our electrons and our different how many electrons get transferred. It's all about trying to end up looking like a noble gas. So which of these has the same number of electrons as a noble gas element? We have silver, we have zinc, we have scandium. And so when we look at our periodic table, we were talking about silver and zinc and scandium. Now scandium was a zinc was a +2, so it lost 1 electron, 2 electrons. Doesn't look like a noble gas. Silver was a +1, it lost 1 electron. Doesn't look like a noble gas. Scandium, on the other hand, lost 3 electrons, so it went 1 and 2, and then when it loses its third, it's got to go all the way over, and it's going to look like this one, 18. Now, argon is a noble gas, and so scandium is the only one out of these 3 ions that looks like a noble gas. And so that's how you kind of put those together. Okay. Now, the reason why these charges are important is we're going to start introducing our compounds. So an ionic compound consists of a positively charged and negatively charged ion. Now, these ionic compounds, what's nice about them is when you put them together, they're going to be neutral. So that means that their charges have to be balanced. So our positive charge should balance out with all of our negatively charged. Now, generally speaking, write your positive ion first, and then write your negative ion when you put these together. So there's a couple of different steps towards making a molecule. And so I'm going to show you 2 different ways. The first part is look at what ions you have involved. So in this case, we're going to look at calcium and phosphorus. Now, we would like to balance out those charges. We would like our calcium and our phosphorus, when we put them together, to be neutral. So if we put 1 calcium with 1 phosphorus, that's not going to be true. The 2 positives is not going to outcome those 3 negatives, and so we're going to be a -1. We have more negative charge there. Instead, we have to adjust how many calciums we have and how many phosphoruses we have, so that way they can find a balance. If we put down 2 calciums and 1 phosphorus, we end up with 4 minus 3, and so now we have too much positive charge. So it's all about finding the right balance between them. So one way to do that is what we call as the cross-multiply system. You take the number of the charge of the negative one and you put it behind the number of our positive cation. You then take the cation's charge and you put it behind our anion. I call it the crisscross method because you basically criss and cross them. And so this tells us how many calciums we need and how many phosphoruses we need. Because if we check this, we would have 3 calciums, each one is a 2+. We would have 2 phosphoruses, each one with a 3-. So that becomes 6 plus minus 6, which is going to be a 0. So we are going to be balanced there. And so you can use that to find out how to make a neutral ionic compound from any 2 ions. Now, the only caveat to this is that if you have something, like let's take tungsten 4 and oxygen, if you do the crisscross, we would get W2O4. When we're trying to write out that compound, we should always simplify. What that means is that because we can fit a 2 into both the W2 and we can fit a 2 in the O4, then instead of writing it as W2O4, we should have it as WO2. So we want to make sure that we end up with the lowest ratio. Not ration, you should have a ratio. So keep that in mind as you go. Now your ions could be an individual or they could be what we call a polyatomic. So a polyatomic ion just means that we have a group of ions all together and they're giving that charge. So a positive polyatomic ion would be ammonium. Ammonium is saying that that entire set of nitrogen and the 4 hydrogens, all of them together has a +1 charge. Sulfate is an example of a negative polyatomic. It's saying that those 4 oxygens and that 1 sulfur has a -2 charge. What I would say first is go ahead and just practice with just your elements. So use this charge, go through and try to balance them out and see what chemical formulas you guys come up with. So go ahead and do that. Pause the video, fill all those in. Think about what charges they should be as you're going through. Your answer is going to look just like this. So we're going to stop there for this video for now. I'm going to come back and we're going to talk about how you name those compounds. But first, I just want you to practice with these, making your ionic compounds. Good luck.